Okay, so what we're going to do now is we're going to look at our GCSE trigonometry. So this is for AS level students who have forgotten what they did in GCSE, or they just need a quick reminder. And then in the second part, then we'll be doing the AS level trig. So if you're doing your GCSEs, then this video will help you as well, because it'll be new stuff for you and hopefully give you an introduction to trig and what it's all about. So why is trigonometry important? Well, what they did in ancient times was it was difficult to, say, measure the height of a tall building. But what you could do is they found that if they had, say, the pyramids like that, and this had the sun over here, that we know that the sun would cast a shadow of the building. So if we were to have a shadow here of the building, then they would look and go, well, if we were to put a stick in the ground, so let's say that this was, we didn't know how high it was, but we took a stick, which we did know the length of. So let's say we took a 1 meter stick and we put it in the same direction, and we noticed that it also casts a shadow, say like this. And what they figured out was that if the sun is going at an angle, it casts a shadow. So the rays will come and it'll cast a shadow like that. And so if they go downwards from the middle, what they have is a right-angled triangle. And then this one would come at the same angle and also have a right-angled triangle. Now, what's important with trig is that these angles were the same. And so what they know or knew is that if you have a right-angled triangle with the same angle, then all of these sides are in the same ratio. So they said, well, they could then measure out the bottom, so they would walk along and they could say, okay, so it's say 200 feet, or let's say 200 meters, because we are using the metric system. And then they could say, well, this is 1 meter long stick, 1 meter long shadow. And they go, well, if this is 1 meter thick, 1 meter long shadow, and then they said, well, we know the length of the stick is, say, 50 centimeters, which is half a meter, then they know that the short side here, the 50 centimeter, is half of the long side, because it's 50 centimeters is 0.5 meters, so it's half. And so then they would know, okay, so the height would be half of the shadow that they measured. And so they would look and go, okay, so this is 200, half of that would be 100. And so they would know that the height of the building is 100 meters. We can see how trig would be interesting. And so now we go on to how we now turn this into a mathematical theorem, which Pythagoras did. So they already knew that there was a relationship, but Pythagoras figured out that if you have this right angle triangle, if you looked at some notation here, the side that's opposite to the right angle in this triangle is called the hypotenuse. And he figured out that if you were to draw a square here, and then a square on the two small sides, what he found out was that the two small squares would add up to the size of the large square. So if I was to try and do this, we'll see, hopefully it works out nicely. So in other words, if we square this, so let's say this is 5 here, 1, 2, 3, 4, 5, then along this way would be then 5, because it's a square. And so this would be 5. And then we know that there's 25 squares here. If you count them all up, you can do that while I'm drawing this if you want to check. Then what he found was that these lengths were 4, then this and this was 4. We could have then 16. 1, 2, 3, 4, 5. 4 times 4 is 16. And then here we have MD1. See, doing this freehand, but it does work for any right angle triangle. This theorem, we have a 3 here, and so there's 9. And we see 9 plus 16 is 25. And so this works for any triangle. This is a nice round number, but it's not always going to be a nice round number. But basically what we know is I'm calling this red one the small side 1. I wrote there small side 1, which we could call A. So maths is all about turning things into letters to make it easier to write. But just think of A as being the small side. So A squared plus the other small side, which is we call B, small side 2, B is equal to the hypotenuse. In other words, the long side. And so we get this theory, this nice little theory, and if we want to give a reason, we call this Pythagoras in honor of the guy who figured this out. So he took what the Egyptians had done and he took it one step further and made this beautiful mathematical theory that works for any triangle, and it's very, very handy. So this means you could also get the small side squared. So let's just look at if we would put numbers in here. So what we're saying is 9 squared, what we had here, plus our, sorry, not 9 squared, 3 squared. 3 squared plus, for a lot of you guys, this is very basic, but it'll get more tricky. So hold your horses if you're getting bored, maybe just skip a little bit, but we'll try and cover everything so that anyone who's kind of struggling with trig, if they watch this, will be able to then understand it fully by the end and not have any gaps in their knowledge. And so we see 9 plus 16 equals 25. Let's see, that says look like 6. And this also allows us to work out the small side. So if you're given any 2 sides, you could work out the other side. So even if you were given, say, the hypotenuse and a small side, you could say, well, we take this formula, you can say a squared is equal to h squared minus b squared. And so what we've done is we've taken the b to the other side and it's become a minus, okay, b squared. And again, you could put the reason as Pythagoras. So that's Pythagoras' theorem, okay? Just to recap on that, I'm not giving you any examples because you should know that already. Otherwise, go and check out some other videos. But this is just a recap. So this comes to the idea that similar triangles have the same ratios, okay? And so we've really kind of covered this in the introduction, but if these are similar triangles, so in other words, a similar triangle means they're in the same ratio. In other words, like Minimi and Austin Powers, he made an exact clone of himself, like 1/8 the size. These are clones of each other. It's just one is bigger, but they've got the same proportions. And so in other words, if these were all sort of, say, 1, and let's say this was, let's make it a nice Pythagoras thing. So if this is 3, 4, and 5, if this happened to be 6 and these were similar, then everything would be doubled. So it'd be 6, 10, 8. Okay, this kind of looks like a 6, 10, 8 as well. But you can see if it was triple the size, it would be 9, and you would times the 4 by 3, and so you could have a 9, 12, and 15. So all in the same ratio. So that is the idea that all these triangles, if they're similar, and in other words, if they're similar, they all have the same angle. So that would be a theta, and this would be a right angle, and this would be a right angle. Okay. And so we could even make this something like a different sort of number, like we could make that 6. Okay. And so 6 is 4 times 1.5 gives you 6. And so then you'd say 5 times 1.5. And so this would be a 7.5 here. And then the yellow would be a 3 times 1.5, which is 4.5. Okay, and if you look at these, they'll all be in the same ratio if they're similar. And this is the kind of the moving on from the Pythagoras, this is the next stage. And so now what we're going to do is we can look and say, well, if I know these ratios are the same, I can now start to work out the sides on any angle. And so you need to know that the ratios between these angles are given a name. And so now we're going to go to our next bit, which is remembering the ratio, so SOHCAHTOA. So let's now look firstly at the context of what this SOHCAHTOA relates to. And so we'll draw our right angle triangle. In fact, let's draw, we'll draw our right angle triangle. And we'll say, okay, now let's do an angle. So there's a theta here. Let's do the theta in we'll do it in red. So if we take the theta as the reference angle, sometimes this is called x. So in other words, the one of the angles that's not the right angle. So we're just going to call this theta. And so that's a notational thing. Then we look at this angle, and this is the angle that we are questioning. And we're saying, well, what are the ratios in terms of this angle here, this angle? And so we then look and say, well, if we're talking about this angle, then this side is opposite to that angle. And so that is what we get, we call the opposite side to the angle we're working with. So this is the opposite, and so we call that O. Okay, and you can see that I've drawn in blue is the O. So we're going to see how this relates to the triangle. Now we have the side. So the sorry, that's the sin first. Then next to this angle, we call this adjacent to this angle. There's a adjacent, which is actually orange. So this is adjacent. I've done a capital A here. Maybe I'll do capital just because it's easier to distinguish between the O's and the A's. And then we have the hypotenuse, which is the long side. And so when we learn about sin, cos, and tan, you probably heard those names, you maybe know already. When we're talking about that, we're talking about it in relation to a right angle triangle. And so let's just go over that again. So we have an angle theta in red. Opposite to that angle is this side here. And then adjacent to that angle is the side here. And then the hypotenuse is the long side. And so once we know that this is the terminology, so if I'm talking about an angle, and I'm say given that angle and maybe one of the sides, I could actually figure out the other lengths, just how the ancient Greeks used to do. So we get to this sin. Oops. Get to the sin cos tan. And so we have sin of the angle, cos of the angle, tan of the angle. And so we can then go sin theta is opposite over hypotenuse. And this is something we have to remember. So these three colors here, the red, blue, and pink are the formulas that you kind of remember. And there's always three things, right? There's always three things. You have the angle and then two of the sides. Well, you actually only need to know an angle and one of the sides, and then you can work out the missing thing. And so we have adjacent. And so if we look at sin theta, that first one, what have I done here? Sin theta equals opposite over hypotenuse. In other words, if I have the angle and I have the blue, I could work out the pink. And if I had the pink and the blue, I could work out the red angle. And so we know if we memorize these, we just have a sign button on our calculator that then allows us to then figure this stuff out. And same with cos. So this is where this rhyme comes, SOHCAHTOA. And that's how you then write these down as what you need to remember when you're doing trig. Other people can remember it as some old hippie caught another hippie tripping on acid. That's one that my teacher taught me. SOHCAHTOA. Much quicker to say. And so the tan is the T over the A. Okay, so now let's look at some examples. So let's just have a look at this. So this gives us our ratio. So this doesn't necessarily tell us our sides because we're not working with a triangle, but this is just when you start using your calculator, how you would put these values in. Okay, so what we're going to do is we're going to get on our calculator, and all we're going to do is do a calculator exercise to say, can you use your calculator to work out the ratio? Okay, so now this is to figure out what x is, right? Because you've got sin 37 as x, which means x is equal to sin 37. So can you put sin 37 into your calculator and see what do you get? What do you get there, Liam?
0.55.
0.55, right? So you know that the ratio of the angles would be 0.55, which means that you would have actually 0.55 over 1. So if you were to have so we remember that sin is some old hippie, so opposite over, what was our opposite in? Opposite was, yeah. So opposite over hypotenuse. So you can imagine the 0.55 would be, if it could technically be over 1, because 9 is actually just 9 over 1. And so if you were told this, you could then have h here. And so if your hypotenuse of your right angle triangle was 1, then you would know that your opposite to that, to say, now, if this was, say, 37, because that's our 37 here in red, then the opposite to that 37 would be 0.55. So this is simply a ratio. It would depend then on the size of the triangle, what we would have. So in other words, if the hypotenuse was 2, then your opposite would be double the 0.55. Okay, so any angle with 37 has the same ratio. So I just said, well, you could make this a 1 and you could have your hypotenuse as 1. But if your hypotenuse is 3, then this would be 0.55 times 3. So if you know your ratios, then it's just a matter of looking at the size of the triangle and deciding what your values are. Okay, so what do we get when we put in cos 37?
0.84.
0.84. Nice. Okay, so then we would know that because this is 37 and you're adjacent, so this could be cos, and so we know that cos is 0.87. What did we do the cos in? It was in yellow. 0.87 over our 1, right? And so if it was a triangle with a hypotenuse of 1, then this would be 0.87. Okay, now let's do tan 37. What do we get there?
We get 0.66.
0.66. Okay, so that would be the ratio of, now when we go to tan, tripping on acid, right? So on acid, so O over the A, which is the adjacent. Now what I want you to do quickly to test this is do your O over A. So put 0.55 divided by 0.87 and see what you get.
I get 0.63.
0.63. Now that's because of rounding. It should be about zero, like obviously with rounding, if you did your exact numbers, you would get to 0.66. Okay. So if you took your exact numbers that you got, obviously you rounded, you would get the value of 0.66. So basically that over that is going to give you the tan, because the tan is opposite, 0.87 over 0.55. So if you're at home and you want to just check that, you can do them with your like 4 decimals and see you'll get the right value. Now what's sine 53?
7.4.
Nope. Sine
0.7. 0.74.
0.74.
74.
That sounds weird. What's cos 37?
.84.
And sine 53?
0.74.
This adds up to 90. These should be the same. Should be the same ratio. Have you got it in degrees?